Last time we talked about the different profiles, and in order to characterize some impurity profile, we have to follow the steps. Like, first we measure rho S, okay? We can do this with a 4-point probe. And then we measure junction depth. We can do this with the ASR, automated spreading resistance, automated spreading resistance, or we can do this by SIMS, okay? And then we can calculate the average conductivity, like the sheet resistance, and then junction depth, okay? And finally, we can obtain the surface concentration from Irwin's plot. Okay, then what it says is that if we can determine the NS and we know the junction depth, okay, and the profile here is going to be Gaussian or complementary error functions, okay, depending on whether it is done by drive-in process or the pre-deposition process. So this is all we have to know about the impurity profile. And the first example has been given here. And in this example, we come to know that the average conductivity is 16.7 ohm centimeter, and from the Owens plot, we know the surface concentration, like 4 times 10 to the 18th. So we have a 4 times 10 to the 18th as the surface concentration, and the junction depth is the 3 micron, which is given. And at that junction, the concentration is going to be 10 to the 15th. That is the substrate doping level. So the profile is going to look like this. That is the example that we have done last time. Now, the second example is given here. Design a pre-deposition and drive-in process for bipolar transistor base region such that the sheet resistance is the 50 ohm and the junction depth should be 10 to the 15th. Oops. The junction depth xj has to be given here, and that is 3 times the 10 to the 4th. That is a misprint. That should be like junction depth is going to be 3 times 10 to the 4th as the first example, right? Centimeter. And the base concentration is going to be 10 to the 15th. That is the substrate to doping, okay, per centimeter cube. That is the misprint, okay? So to make this kind of junctions, we have to design the pre-deposition temperature and time, excuse me, and the drop-in temperature and the time. Temperature and time, okay? So how do you do that? You just assume that boron is used because it's a P-type, the only dopant used in the industry is a boron, and the pre-deposition temperature is 950. That's a typical number. And the drop-in temperature is 1,000 degrees centigrade. We just assume it. And then we begin to calculate, see if we have a reasonable time to get this profile, dopant profile, okay? And average conductivity is going to be 67 ohm centimeter. And from the Owens plot, we can get the surface concentration is 2.3 times 10 to 19. So this is the actual profile that we want to have in this question, right? The surface concentration is 2.3 times 10 to 19th, and the substrate doping is 10 to 15th, so that the junction, at the junction 3 micron, this Gaussian profile at this point will have the concentration 10 to the 15th. And we just assume that the pre-deposition temperature and the drop-in temperature, and we want to calculate how much time we need to have this profile. That is what we are going to do, okay? So after drop-in, the base is assumed Gaussian, and we know the profile is going to look like this, right? And at the junctions, the concentration is 10 to the 15th, so that the concentration 10 to 15 is going to follow this equation, and we can calculate the dt, which is 2.24 times 10 to the minus 9 centimeters square. And the drop-in is done at 1100 degrees centigrade. Oops, that we assumed that this is the wrong print then. That we assume the drop-in temperature in this calculation like 1100 degrees centigrade, okay? So we just plug in the drop-in temperature at 1100, then from the table we know the diffusion coefficient is 3 times 10 to 13, minus 13, okay? And then you plug in this number to this equation, then we can get the drop-in time, which is 2 hours, about 2 hours. So if we do the drop-in at 1100 degrees centigrade for 2 hours, then we can have this diffusion profile. And that is not that bad, okay? If we decrease the temperature like 1000 degrees centigrade, then we can have the drop-in time longer than 2 hours, even 3 to 4 hours. That is also reasonable, because in the industry we put a 100 or 200 wafers at a time. So this time for the drop-in, that is not that critical parameters in the industries. Okay, that is nothing to do with the throughput, because one time is a batch process. We put 100 wafers at the same time, and after 3 hours or 4 hours, we have 100 wafers, so that this time we have is not that critical. Anyway, so now we have to determine the pre-deposition conditions, And in a predeposition, the amount of charges, the amount of dopants loaded during the predeposition is to be this equation, and we can calculate the charges during the predeposition, which is 1.93 times 10 to 15th. So if we have a complementary error function during the predeposition, we know the xt and the q, and if we are going to do the predeposition at 950 degrees centigrade, and the solubility, the concentration of the surface is going to be 2.5 times 10 to the 20, and the diffusion coefficient from the table is 9 times 10 to the minus 15. So we end up with the time necessary for the predeposition is 1.4 hours. Maybe this is a little bit long that we expect to have, because during the predeposition, the source has to be continuously supplied. And if you supply the source for this hour, maybe it is not that trivial question. And I mean, it may be long. So if you want to shorten the predeposition time, all you have to do is crank up the temperature, predeposition temperature. And here in this calculation, we set the predeposition temperature as 950 degrees centigrade, and drive-in we have about 2 hours. That is reasonable. And the predeposition, if we assume that we are going to do this at 950, then we end up with 1.4 hours, okay? That is a little bit long. So we can increase the predeposition temperature to 1000 degrees centigrade. And I didn't do the calculation, but I'm sure the predeposition time is going to be shortened to the 1 hour or so. And that is reasonable. So the approach we are making to solve this problem is that first we have to assume the predeposition temperature and the drive-in temperature, and we get the profile from the Owens plot by measuring the junction depth and surface resistance. Then we can calculate the time necessary for that profile for each drive-in and the predeposition, and then see if it is reasonable. So if it is reasonable, then our assumption is okay. But if it is too long or too short, we can adjust the temperature. Okay? That's what we should do in designing the diffusion process in the semiconductors. Okay, now let's move to the next topic shown in the book, which is the advanced topics in the diffusion in the semiconductor. And the 3 items is given in this book, okay? The first is the lateral diffusion, and the second thing is field-aided diffusion, field-aided. And dopant enhanced diffusion. Okay. The lateral diffusion is that when we do the doping in the semiconductor, you want to localize the doped area. Okay. So how do you do that? You have an oxide, a deposit or grow the oxide, and then using the lithography, you just get a pattern like this, and then you put this thing. This is a wafer, and the furnace, so that only this part, we want only this part to be doped with the dopants. Okay, so we want to have profile something like this. Okay, and this is the doped area. So dopant atoms is going to diffuse from the top to the vertical, something like this, but this dopant atoms is going to diffuse into the silicon not only along the vertical directions, but also is going to diffuse underneath the oxide, the lateral directions. And this is not what we want. We do not want this. Okay? Well, but we call this the lateral diffusion. And in the book, it says it's about 0.8 times the vertical diffusion. It's not trivial at all, right? So this is the design that we have on the mask, but unwanted diffusion is going to happen underneath the mask, underneath the oxide, so that the junction width is actually not this, but it's going to be this, A prime. Okay? So this is not what we want, but it happens in the diffusion process. And it turned out to be about the 0.8 to the vertical diffusions. And field-aided diffusion is that it doesn't happen in a metal, but in a semiconductor or insulator case, the dopant atoms is going to be ionized in a fashion that if you have donors, then it's going to be ionized to be itself is positively charged, and then it gives up the electrons to the conduction band. That is the donors. Okay, acceptor case, that it's going to be negatively charged and then produce the holes. Okay, that is acceptance. So this ionized ions is going to diffuse in the silicon or in the host matrix, not the neutral species as in the metal. In case of metal, actually the same thing happens, but this ionized donors or acceptors or impurities, I should say, in the metal is going to be screened with the abundant free electrons or free holes, so that this doesn't have this impurities cannot have charges by itself. But in a semiconductor or in an insulator case, we do not have that many free electrons and free holes, so that the donors have to be in the state of, in a charged state. It does have a charges by itself. So when it's diffuse, then it should be, if there is a field, then it should have an effect of the field. Now, for example, if you have NPN bipolar transistor, something like this. Okay, then this is the emitter case, and the N plus, and this is the base, so that this is the P minus, and the substrate has been doped with the M minus, so that it is going to have NPN bipolar transistor, right? Bipolar transistors. In this case, if you have a P minus here and then you want to diffuse the M plus or the subsequent diffusion process, this M plus ions, okay, which is positively charged, then it is going to travel along the P minus here, and then the P minus doesn't have a uniform profile of the dopant, so that if it does have a profile something like this, it means that we do have more negatively charged ions here and the less negatively charged donors, acceptors here. So we should have minus and plus electric field by this dopant acceptor profile in the base region. So we do have this field, electric field in the base region, and then with this electric field, this positively charged donors now is going to be diffused, so that this field is going to affect the diffusion of the charged donors, positively charged donors. And what can you say if it is a minus and plus, and the positively charged ions is going to diffuse through this, then it should be retarded, right? If it does have this kind of electric field, then it's going to work as a retardation of the diffusion of the positively charged ions. Okay, that is the field-aided diffusion. Now, this field-aided diffusion in this book, the effect has been calculated, and it turned out that this effective diffusion coefficient is going to be the diffusion coefficients including the field effect, and this diffusion coefficient is just the chemical diffusion coefficient. So this is the correction factor, okay? The correction factor, if you look at this carefully, you can see that this correction factor cannot exceed more than 2, okay? So this field effect, it cannot be more than 2 times than the chemical diffusion coefficients that originally the dopant can have. Okay? But it's not a trivial question at all, because in a bipolar transistor like this, the base region now is going to be from here to here is the base width. Okay? And this base width is critical for the bipolar transistors. The efficiency of the bipolar transistors is very much dependent on the width of this base. So we want to have the base as narrow as possible. And this field-aided diffusion, if it works as to enhance the diffusion of this emitter thing, then we are going to have the increase the width of the base region, and it is going to affect the efficiency or the gain of the bipolar transistors. By the way, this lateral diffusion case, this is critical for the MOS transistors, Fielded diffusion, as I said, is critical for the bipolar transistors. Okay? And the reason why this lateral diffusion is critical for the MOS transistor is that when you have MOS transistors, you're going to have the source and drains and gate, something like this, okay? And this, I just draw this thing is just aligned to the edge of the gate, but if you do this source and drain by the diffusion process, then the lateral diffusion is going to be done underneath the gate, something like this. And this is not what we want. Unwanted diffusion happens through the lateral diffusion. Now, this is called the channel length, okay? In bipolar transistors, the base width is critical for the functions, but in MOS transistors, this gate length is critical. And this gate length is going to be determined by the lateral diffusion of this source and drain diffusion process, right? So if this lateral diffusion is going to be around 0.8 times of the junction depth, that is not trivial at all, because these days this gate length is sub-micron. It's less than 1 micron. 1 micron. Okay, so this prevention of this lateral diffusion is very important in the MOS transistors, and the effect of a fielded diffusion. At most, even though at most it is about 2 times of the chemical diffusion, that is going to be critical in bipolar transistors. The final topic for the advanced diffusion is a concentration-dependent diffusion. Okay, that is dopant-enhanced diffusion is the same thing to say concentration-dependent diffusion. It has been found that if you do the diffusion, if you measure diffusion coefficients, especially in case of a phosphorus, when you have a heavy concentration of a phosphorus in the silicon, the diffusion coefficient of phosphorus in the heavily doped silicon has a very high, abnormally high diffusion coefficients. That is going to be the concentration-dependent diffusion. And the main idea related with this is that in the substitute, in the dopant diffused in the silicon matrix by the substitutional diffusion. Okay, dopants are diffusing in the silicon by substitutional. Okay? What is substitutional diffusion? The dopant atom has to be coupled with silicon vacancies for the diffusion process in the substitutional diffusion. That is the difference from the interstitial diffusion, right? Interstitial diffusion. That is this is the difference from the interstitial diffusion. So substitutional diffusion is always slower than the interstitial diffusion, that we know. Okay, because of this, because the substitute dopant atom has to be coupled with the vacancies. Now, this is a semiconductor, so that these vacancies of silicon can have a charge. Can have a charge. Because this semiconductor is a lack of free electrons and holes. So now this vacancy of silicon can have many different charged states as shown in the note. You can have singly negative charged states or doubly negative or singly positive and doubly positive charged states. You can have all these charged states depending on the Fermi energy levels. Because the ionization, it requires the ionization of neutral vacancies. The ionization energy is different. And if that is close to the Fermi energies of that specific system, then among these charged states, one of them is going to be the dominant compared to other species. Okay? And in the real practice, we've never seen this doubly positively charged silicon vacancies. So depending on the Fermi energy level, that means depending on the types of silicon, N-type or the P-type, this dominant species of the vacancies is different, and this differently charged states is going to couple with the dopant atoms to be diffused in the furnace, so that the diffusion coefficient now is going to be expressed not just single number, but it's going to have a neutral diffusion coefficient and singly negatively charged diffusion coefficient, doubly negatively charged, and positively charged species. And in this equation, you can see that there is no contribution from the doubly positively charged vacancies, because we never seen that in the experiments. Okay, so now diffusion coefficient is this much complicated. You can see the diffusion coefficient, and it's going to be enhanced the n squared. That n is the dopant concentration. Okay. So if you look into this equation carefully, then you can see that if the dopant atoms is going to be coupled with this, then that is going to contribute to the part of the D minus there. Okay. Now you can immediately see that the donors or acceptors will have different charges. Like donors has a positively charged, and the acceptors is going to have a negatively charges. Naturally, you can see that these positively charged donors are not going to couple with the vacancies, positively charged vacancies. Okay, so among these donors is going to couple with the V minus here or V doubly minus here, but not with this. Okay, so when you talk about the D of phosphorus, then you don't have to count for that part P over N Di plus. This is almost negligible. Okay, and in particular, if it is talking about the phosphorus diffusion in phosphorus doped silicon, now this among these, it turns out that the diffusion coefficient, the other terms are all trivial, negligible, and only this term survives in the phosphorus case. In arsenic and antimony case, it is not that. Only this part is most important, but in a phosphorus case particularly, only this part is important, so that diffusion coefficient is proportional to the concentration of phosphorus to the square power. So that's why, especially in the phosphorus diffusion case, this dopant effect or concentration dependency on the diffusion coefficient is outstanding. Okay? So that is has been shown in this figure here, and as you can see, the dopant concentration. This is a phosphorus dopant concentration, and this is a phosphorus diffusion coefficient. As you can see, if it is less than 10 to minus 20, at around the 10 to minus 20 or 5 times 10 to the 19th, you begin to see the effect of the concentration in the diffusion coefficient, and it's exponentially it enhances the diffusion coefficient, and that is n square proportionality part. And then you naturally ask a question: why below 5 times the 10 to the 19th it doesn't have any effect? Why? Because this diffusion coefficient has been measured at the 1050 degrees centigrade, and at this temperature, the intrinsic carrier concentration is about 10 to the 19th. You guys know about the intrinsic carrier concentration? Intrinsic carrier concentration. Intrinsic carrier concentration, Ni, is, of course, that is the thermally activated process, and it's very much dependent on the temperature, right? And at 11, that is 1050 degrees centigrade, the diffusion coefficient has been measured. At this temperature, the Ni, intrinsic carrier concentration, is about the 10 to the 19th. Cool. Okay. At room temperature, this is about the 10 to the 12th. But if you elevate a temperature like 1050, then the intrinsic carrier concentration is 10 to the 19th, which means if you dope the silicon with the phosphorus and the dopant concentration is below this, then at this temperature, the doping effect is trivial if the dopant concentration is less than 10 to the 19th at this temperature, right? So the material can feel the doping effect beyond 5 times 10 to the 19th. So after this, the diffusion coefficient is proportional to the concentration to the second power. Below that, the doping effect is trivial because the intrinsic concentration is already about 10 to the 19th, which is corresponding to the equivalent to the doping concentration. So that's why we do see this curve in these experimentally. Okay, that wraps up the diffusion process. You guys have any questions? let's see. Where are we? And in the note, after that, we have chapter 4, pointed effects and silicon. And chapter 5, impurity diffusion profiles, and chapter 6 is the oxidation. So the chapter 4 and chapter 5 is advanced topics, and that is going to be discussed in the graduate courses. So if you are interested in, of course, you can take a look at these chapters, but it's not going to be discussed in this class. Okay, on Wednesday, we're going to talk about the oxidation, the next unit process for VLSI. Okay? All right, I'll see you on Wednesday then.